recorded. Okay, so chapter 3 is all about something called the determinant, which is this really kind of interesting little thing connected to a matrix. So every square matrix, so again, just like with our inverses, we only are allowed to talk about determinants if we're talking about a square matrix. So every square matrix is associated with this number. Could be a positive number, could be a negative number, could be 0. And that number is called its determinant. And that determinant can actually tell us a lot about a matrix. And we'll get into all of that theory. But the goal in this first section is just to figure out the computation part, right? How do we compute the number? And then don't worry, we'll unpack the theory of what that number tells us throughout the rest of the course, really, because we'll learn more and more things about what this number tells us as we move all the way through our very last chapter. Okay, so first of all, if we have a 2 by 2 matrix, A, B, C, D, and I'm going to write it in case that's hard to see online, then the determinant of A is that AD minus BC. And remember, that's the quantity that came up, right, when we were finding our inverse of a 2 by 2, that AD minus BC, so it's that same value. We have some different notations of the determinant. The nicest one, my personal favorite, is just that DET, because then it's super clear that that's what we're looking for. But sometimes you'll also see what looks like absolute value bars. Now, be careful, because I always have someone throughout the course at some point in time confuse this with, oh, I'm going to take like the absolute value of every entry in the matrix or something, but that's not what this means, okay? So if you see what looks like these absolute value bars, that's just a different notation for the determinant, okay? Okay, so for example, then here's some 2 by 2 matrices. So let's quickly compute their determinant. All right, so here's the matrix A, 2, negative 3, 1, 2. So if I want to compute its determinant, it'll be what minus what, or what plus what? 4 minus negative 3, good. So I would do 2 times 2, which is 4, minus 3 times negative 1, which is negative 3. And so I would get 4 plus 3, or 7. Okay, so the determinant of A is 7. I'm going to use that other notation just so you get used to seeing it. If I want the determinant of the matrix B, that'll be what minus what? 4 minus 4, good. So I do 2 times 2 gives me 4. Minus 1 times 4 also gives me 4. So the determinant of B would be 0. And last one like this. What is the determinant of C? 0 minus 6. Good. So 0 minus 6 or negative 6. Cool. Okay. So just a couple of examples, right? So the determinant can be a positive number, a negative number, 0. None of these were fractions because I didn't feel like throwing back fractions into the mix, but the determinant can absolutely be a fraction, right? If this entry, if this was the number 1 and that was pi, the determinant will be pi, right? So just whatever you got in there, right? So it can be rational number, irrational number, but it's just a number that's associated with our matrix. Okay, so 2 by 2s then, not too bad. Let's think about higher order, okay? Okay, so if A is a square matrix, then the minor, Mij, of the element Aij is the determinant of the matrix obtained by deleting the ith row and the jth column of A. All right, that's a mouthful. It's much harder to describe in words than it is to just do the darn thing, okay? So we get the minor by computing the determinant. We delete the ith row and the jth column and take the determinant of what's left. You'll see what that means, what that looks like in just a second. Okay, that's the minor. The cofactor then, Cij, is the minor times this negative 1 to the I plus j. Now this is either a negative 1 or a positive 1, right? Because I'm just taking a power of negative 1. So the cofactor is either exactly the minor or it's the negative of the minor. Okay? All right, so let's do an example so you can see what this looks like. Okay, so so here is just a generic 3 by 3 matrix. We're going to compute some minors and some cofactors. I really want a blue marker. See if I can find one. I want to see red. Aha! Okay. Okay. So M31. So I'm going to find the entry A31. All right. So there's A31. I'm going to delete the row and column where A31 sits, and then take the determinant of what's left. And so in this case, the determinant of what's left would be the determinant of A12, A13, A22, A23. That makes sense. So we delete the row and column containing A31, and then take the determinant of what's left. And since this is a 2 by 2, right, our determinant would be A12 times A23 minus A13 times A22. Okay. Now, for the cofactor, so the cofactor will be -1 to the 3 plus 1 times M31. So -1 to the 3 plus 1 times M31. Okay, but now this -1, right, and the -1 to the 4th power. So is that a -1 or a +1? A +1. So the cofactor and the minor would be equal in this case. Right, the cofactor would also be the same number, whatever this number turns out to be. Cool. Okay. All right, we're going to play the same game with M23. So for M23, we find the entry A23. So there's A23. We delete the row and column that contains that entry and take the determinant of what's left. So in this case, the determinant of what's left would be A11, A12, A31, A32. And then because it's a 2 by 2, that determinant would be A11, A32 minus A12, A31, whatever number that is. For the cofactor C23, we would do -1 to the 2 plus 3 times the minor M23. In this case, since it's a -1 to the 5th power, that's a negative, right? So this time the cofactor would be the minus of M23. So whatever number this turns out to be, right, this is 6, then the cofactor would be -6. This is -7, that'd be +7, right? Cool? Good so far? All right, let's do one with actual numbers. So we're going to find some minors and some cofactors. These boards. Let's see your red thing. Okay. All right, so we're going to find M11, M12, M13, and C11, C12, and C12. All right, so we'll start with M11. So I want to find the A11 entry, right? First row, first column, and delete the row and column that contains that entry. And M11 is the determinant of what remains. 4, 2, 1, 2. 1, 1. I think all that's on camera. Okay. All right, so M11, when I take this determinant, what do I get? 6. I get 8 minus 2. Okay, so I get 6. Okay. All right, for M12, I take the first row, second column, delete the row and column containing that entry. And so what's left would be negative 1, 2, 0, 2. And what's the determinant of that guy? Negative 2. Okay. All right. Last but not least, M13. So there's my A13, first row, third column. Delete that row and column, take the determinant of what's left, which would be negative 1, 4, 0, 1. And what's that determinant? Negative 1. Cool. All right, so we got all the minors, and that's really the hard part. Now we need the cofactors, C11, C12, C13. So we do negative 1 to the I plus j times mij. All right, so in C11, so I have a negative 1 to the 1 plus 1, right? So do I want M11 or negative M11? Just M11, so I get 6. All right, for C12, it's a negative 1 to the 1 plus 2. So M12 or negative M12? Negative M12, so it's a negative 2. Get out of the way so you can see that, right? A negative 2, so a positive 2. And then for C13, it'll be a positive, right? So just M13 again, and M13 was negative 1. All right, so those are all of our minors and cofactors that we were asked to find. Any questions about that? Okay, so now that we know all that, we're ready to define the determinant. Y'all haven't even done that yet? We're ready to define the determinant, and it looks gross, but it's not that bad. Okay, so here's the determinant. If A is a square matrix of order 2 or greater, then to compute its determinant, we're going to focus for right now just on this first definition. We'll come back and talk about what these mean in just a second. Okay. So in this first definition focuses on the first row of our matrix. And what it says is take your very first entry, A11, times its cofactor, plus the next entry in the first row, A12, times its cofactor, and keep working your way across that first row. And every entry you come to, you take the entry itself, multiply it by its cofactor, and then add the whole thing up. All right, so let's do that. Okay, so this is the exact same matrix we had in example 2. Okay, so we have already found our cofactors. Okay, so if I want, we have some words there. All right, so A11, C11 plus A12, C12 plus A13, C13. So that's our definition. Okay. Okay, so A11, that's our entry in the first row, first column. That's the number 3. And we found the cofactor C11 to be the number 6. A12, the next entry in the first row, is the number 1. And we found the cofactor C12 to be the number 2. A13 is the number 0. And we're not really going to need it, right? But C13 we found to be negative 1, so I'll put it there so we can see it in the formula. All right, so we put these guys together. So our determinant would be 18 plus 2 So the determinant of A would be 20. All right, cool. Okay, now, what we did in this example was we expanded our way across the first row. But there's nothing special about that. If we look back at this crazy formula, so this first row, this first piece of the definition, this is what the definition looks like if you work your way across the first row like we just did. It'll ask me again in just a second. Okay, but there's nothing special about working your way across the first row. You can work your way across any row that you like, right? So the second piece of the definition, this is what it looks like if you work your way along the ith row. But there's also nothing special about working your way across rows. You can also work your way around down any column that you like. And so this final piece of the definition, this is what it looks like if you work your way down the jth column. Okay, so that's what the definitions look like. So let's go back to that same matrix one more time. And instead of working our way across the first row, let's compute the determinant a different way. So let's expand down the second column. What colors? I'm doing something different. All right. So this time we're going to expand down the second column. All right. So our determinant So we start then with this entry, the number 1. And then we've got to multiply by his cofactor, right? His cofactor will be a -1. That entry is in the first row, second column, times the determinant of what we get if we delete that row and column, right? So if we delete that row and column, we're left with the 2 by 2, -1, 2, 0, 2. All right, so that's the 1. Then we go to the next entry, which would be 4. 4 is in the second row, second column. Times the determinant of what we get if we delete the row and column containing 4. So that will leave me with 3, 0, 0, 2. All right, I'll move the camera if I need to. And then I have number 1, the entry 1, which is in the third row, second column. And then times the determinant of what we get if we delete that row and column. So that would be 3, 0, -1, 2. Let me take the camera and make sure I didn't wander off. Let me move y'all just a little bit. Okay. So let's untangle all of those little pieces. Okay, so I have a 1. Is this a +1 or a -1? -1. And what's this determinant? -2. Okay. Then I have a 4. Is that a positive 1 or a negative 1? Positive 1. I'll just put it there so you can see that I did it. And what's that determinant? 6. Okay. Then I have a 1. Positive 1 or negative 1?
Negative 1.
Negative 1. And what's that determinant? 6. Okay. So we have a positive 2, a positive 24, and a negative 6. So sure enough, we get the same answer. We should, right? We should always get the same answer regardless of what row or column we work our way across or down. So we got the same answer that we got when we worked our way across the first row, which is that the determinant of this matrix is 20. They get faster once you kind of get the bottom. Cool. Any questions before we do? We're going to do more, I promise. But any questions about this guy so far? All right, cool. Okay, now, the first thing we're going to make easier is all of these little negative 1 powers. There's a trick to those guys. And it's that a matrix always has this checkerboard sign pattern. So, for instance, in the 3 by 3 case, it will always look like this, right? So it'll always be plus this guy, minus, and then plus if you're working your way across that row, minus, plus, minus, minus, plus, minus, just depending on whether you're working across or down, right? So it's this checkerboard, and it works the exact same way in any size, right? You always start the very first entry is positive, and then you just alternate pluses and minuses as you expand down and across. Cool? So that way we don't have to worry about those negative 1 powers. Or we just think about the checkerboard. Okay, so let's do a couple more. All right, so here is another 3 by 3. We can work our way across any row or down any column. What looks good to you? There's no right or wrong answer. Which one looks the most appealing? Sean, which one you want?
Row 3.
Row 3. Looks good to me. All right, so we're going to work our way across row 3. I'm going to come over here just to have a little bit more room, but I may need to move my camera back. Okay. All right, so let's compute. Oh, wait, let me put some words. Otherwise, Dr. Pines will come running in here and be like, why are you being so rude and just like diving in with symbols? I'm sorry, Dr. Pines. Okay, so if we think about our checkerboard, right, I start positive, so it would be positive, negative, positive. So I start with a positive 2 times the determinant of what I get if I delete the row and column containing 2. So that will leave me with 1, 2, 4, 2. So the determinant of 1, 2, 4, 2. All right, if this guy was positive, then the next one would be a negative. So I would do minus 3 times the determinant of what I get if I delete the row and column containing that 3. That leaves me with 3, 2, negative 1, 2. And last but not least, so it was a positive, negative, positive. So it'll be a positive 1 times the determinant of what I get if I delete the row and column containing 1. So 3, 1, negative 1, 4. All right, let's see what we get. Okay, so what's the determinant of this guy? Negative 6. of this guy, 8. And determinant of this guy, 13. All right, so let's see. So we get negative 12 minus 24 plus 13. All right, so that's 1 minus 24 looks to me like minus 23. That look right to everybody else? As a cute little just reminder, remember your cross product from back in the day, right? Remember you expand along the first row, right? I times BF minus CE. There was always that really annoying minus J, right? Minus J times AF minus CD plus KAE minus BD is just the determinant, right? So the cross product that you were computing back in your multivariable calculus class, you were just computing the determinant where you expanded across the first row. And that's why it was always a minus J, was because of that checkerboard pattern. So kind of a cute little connection. You haven't seen it before. Okay, now we've been picking on 3 by 3 matrices a lot. Uh-oh. All right, so let's go bigger. Now, in theory, you can work your way across any row or down any column that you like. But in practice, it might be to our advantage to be strategic, right, about which one we pick. So when I look at this matrix, is there a particular row or column that looks like it might be the most appealing to us? Column 3, you're absolutely right, because it's got all those zeros, right? So if there's a row or column that has some zeros, be nice to yourself, right? I mean, you don't have to, right? In theory, you can work your way around any row or column that you like to get the exact same answer. But if we got to do it, right, then we might as well be nice to ourselves. So let's work our way down that third column. Let me use a different phrase. We can compute. And I'm going to use that absolute value bars just so you see it. Okay, so think about our checkerboard. I'll start with the positive, right? So positive, negative, positive. So I'll start with a positive 6. And then I need the determinant of what remains when I delete the row and column containing that entry. And in this case, I get a 3 by 3, right? Not my little 2 by 2s, unfortunately. So I'm going to need the determinant of 276, 151, 377. We'll come back to that. Okay. All right, so there's my 6. And again, right, positive, negative, positive. So when I go down, the 3 will be a negative, right? So it'll be a minus 3 times the determinant of what I get when I delete the row and column containing that 3. So that'll be the 2 by 2 matrix, 2, 6, 2, 1, 5, 1, 3, 7, 7. Wait a minute, something's wrong. Oh, never mind. I thought they were exactly the same, and I was like, that shouldn't happen, but they're not, so we're okay. I think we're good. They were so close that it threw me off. I was like, wait a minute. That's something else, but that was good. Okay, all right, so I have 6 times. Okay, now I've got to compute the determinant of this guy. So what row or column do y'all want to work with? column 1. Sounds good. All right, so I start with a positive 2 times the determinant of 5177. Then it'll be a minus 1 because of my checkerboard. Minus 1 times the determinant of 7677. And then plus 3 times the determinant of 7651. All right, so let's do this piece together, and then let's all do the second half, and then we'll put it all together. Agree. All right, so let's see. So I have 6 times 2 times. All right, so this is 35 minus 7. So that's what, 28? Minus 1 times 49 minus 42 plus 3 times 7 minus 30 negative 23. Does that look right? My arithmetic look all right to everybody? All right, so that's the first half. All right, you guys take a second. You can use any row or column that you want, right? So if you want to stick with first column, you may. If you want to change it up and do a different row or column, feel free. So take a minute and see what you get from this second half of things, and then we'll all come together. Give you guys a chance to practice. nothing special about that. If you did a different row or column, you should have gotten the same answer, right? So I had a +2, -1, +3, and then the appropriate determinant. And for all of this piece, regardless of what row or column you work with, it should have simplified down to 16. All of this gross stuff that we did originally simplified down to -20. So -120 minus 48. So the determinant of this glorious 4x4 matrix is -168. Cool. All right, good. Now, the good news is your calculator does have a determinant button, right? So if you have a nice just numeric matrix like this, you can use your calculator to compute the determinant of that matrix, okay? But you need to make sure you're comfortable with doing it by hand, because y'all know on an exam, I'm not going to give you all numbers, right? I'm going to have X, a Y, and Z in there, something like that. So you got to do it by hand using the formula. So make sure you're, but it won't be anything this gross, okay? But I just wanted you to see what one looks like when it's big, big, big. And of course, 4x4 is not even big, 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 but as big as we're going to go doing it by hand. Cool. Okay, any questions so far? All right, let's start learning some things that can make our lives easier then. All right, so here is going back to a 3x3. All right, now which row or column looks particularly appealing to you about this matrix? Maybe the first column, all those zeros, okay? So, all right, so let's see. So I agree. Let's determine the determinant of A. All right, so we start with a positive in our checkerboard. So that would be a +3 times the determinant of 2, 3, 0, 4. And then it would be a -0 times something plus a 0 times something, right? Okay, and so then we would have 3 times this determinant, which is what? 8, right? 2 times 4. So we get a determinant of 24. Okay, so here's what I want you to notice. That the determinant that we found, this 24, is actually equal to the product of the entries down that main diagonal. Right? It's just 3 times 2 times 4, which are the entries down that main diagonal. Well, A is a special matrix. It's what's called an upper triangular matrix. And we'll define these formally in just a second. But what that means is, in an upper triangular matrix, there are entries, well, let me do that backwards. In an upper triangular matrix, every entry below the main diagonal just consists of zeros. Okay? Let me give you a more formal definition here. Okay? So, in an upper triangular matrix, that's like the kind that we just saw. Okay? You've got whatever you want down this main diagonal, and whatever in the world can be happening up above that diagonal, but below it, there's nothing but zeros. So, for example, so I can have anything I want happening kind of above this main diagonal, but everything below that diagonal has to be zero. So everything that is below, there's my main diagonal. Everything below the main diagonal has to be the zeros in an upper triangular matrix. In a lower triangular matrix, it's the opposite. So I've got my main diagonal. And whatever can be happening down here, I don't care. But everything above that main diagonal has to be zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, leads you to 1. So everything above the main diagonal has to be 0. So an upper triangular matrix and a lower triangular matrix. And then this here, which may be a little bit hard to see on camera, says that if you are either upper or lower triangular, then computing the determinant is really easy because it's just the product of the entries down the diagonal. So if you are a triangular matrix, then your determinant is just the product of the entries down the main diagonal, just like we saw in the last example. So here are a couple of examples for us. So A is an upper triangular matrix. And so if I want to compute its determinant, I'm just going to take the product of the entries down the diagonal. 2 times negative 1 times 2 times 5. So the determinant is negative 2. Similarly for B, because B only had entries on the diagonal, it's technically a diagonal matrix. So it's both upper triangular and lower triangular, so it's just a diagonal matrix. So to get its determinant, I'm just going to take the product of my entries, right? So negative 1 times 2 times negative 3 times 5 times negative 4. What's 5 factorial? 120, and positive or negative? Negative. So just the product of the entries down the main diagonal. Okay, now, before we leave this very computational section, I will tell you one other thing. There is an alternate method for 3 by 3 matrices, and it goes like this. So if A is a 3 by 3 A, B, C, D, E, F, G, H, I. So I've got a 3 by 3 matrix. There's a trick for 3 by 3. So what you do is you copy over your first 2 columns, which that should be a D, excuse me. You copy over your first 2 columns, so A, D, G, B, E, H. And then, so you multiply down these, starting with the main diagonal. So A, E, I plus B, F, G plus C, D, H. So you multiply going down the main diagonals. And then you subtract going up. So GEC minus HFA minus IDB. All right, so just so you can see that method in practice. And you have to use this, but some students love it. So if you love it, then go for it. -142. So here's an example of using this other method. So here's a 3 by 3. So we copy over our first two columns, 3, -1, 0, 1, 4, 1. So we multiply down the main diagonals. So 3, 4, 2, 1, 2, 0, 0, -1, +1. And I'm going to write all that down just so you can see it. So 3, 4, 2 plus 1, 2, 0 plus 0, -1, 0. So going down those diagonals. And then we're going to subtract going up. So 0, 4, 0 minus 1, 2, 3 minus 2, -1, +1. All right, so that would be 24 plus 0 plus 0 minus 0 minus 6 plus 2. So 24 minus 4. So like 20 was a very popular number today with my examples, but don't read anything into that other than just kind of a random question. And then I picked a lot of the same numbers, 1, 2, 3, and 4 over and over again. So that's kind of right. So again, just a cute little trick. So if you like it, you can use it. If not, you can ignore it. I always ignore it. I just do it the old-fashioned way, but I don't know. Okay. Any questions on computing determinants using the definition? All right. Good, good, good. All right. Let's start to learn some of the tricks. We learned 2 already. Well, really just 1. That our diagonal and upper triangular and lower triangular matrices are
Hey, Dr. Heller.
yeah.
Someone asked, why is the trick only for 3 by 3 matrices?
Great question. I have no idea. I don't know who found this trick. So I don't know. It's the only one that it works for. Like if you try the same thing with like a 4 by 4, you get the wrong answer. So it only works for the 3 by 3s that you get the right answer. I don't have a good answer for that. Great question, but I don't have a good answer for that. There's probably a different trick for 4 by 4s, or there could be, right? A different trick for 4 by 4s, or that could be a really fun little research project. If anybody wants to play with that, that would be fun. If we can come up with a trick for 4 by 4s, if one does not currently exist. Okay, so we just saw that determining the determinant of a triangular matrix is easy, right? You just have to multiply down the diagonal, and then you're done. And we also know, if we think back to our chapter 1 stuff, right, how to start with any old matrix we want and use row operations to turn it into a triangular matrix. So cool. Let's combine those 2 ideas, okay? So what we need to do is we need to figure out what those row operations do, what that effect has on a determinant of a matrix. So suppose that A and B are any square matrices. Okay, so if I get B from A by swapping two rows, the effect that that has on the determinant is that I get a negative. Cool. So if I swap two rows in a matrix, then my determinant gets a negative. Right? If, this is the best news of all time, if I take A, I add a multiple of one row to another row, and that's how I get to B, that does not change the determinant at all. And that's great news because that's the trick that we use the most frequently, right? So anytime we add a multiple of one row to another row, it does not change the determinant of the matrix. Cool. Okay, so let's see. We talked about swapping rows. We talked about adding a multiple of one row to another. What's our third row operation? Multiplying by a non-zero constant, right? So what's that going to do? So if B is obtained from A by multiplying by a scalar C, then we want to think about taking that C and factoring out of that determinant, okay? And what did I want to say that specifically? The next slide. Okay. Okay. Now, unfortunately, the full-on proofs of these guys are a little bit beyond the scope of this class. I'm going to give you a little bit of an idea about this first one, just by looking at the 2x2 case, and then we'll talk about what you would do in more general. So I'm writing on the next slide where it says proof ideas, but I'm going to keep the theorem itself up on the board. Okay, so proof ideas, so not full-on proofs, because we're going to look at examples, and that's not a proof, right? Okay, so proof ideas. So property one, let's look at the 2x2 case. So suppose A is the matrix A, B, C, D. It's a nice little 2x2. So determinant of A, right, is AD minus BC. But now, if I swap those rows, so if I swap the rows in A, that'll give me CDAB. And if I look at the determinant of B, I get BC minus AD, which is, of course, the negative, right, of the determinant of A. Okay, so that's the proof in the 2x2 case. That's the baby case, right? For those of you that have had Math 280, that have had a proofs course, what you would do to get to the n by n case is from here, you would proceed by induction. So if you've had a proofs course and you know what in the world I mean by that, that's what you would do, right? So then, again, if you know what that means, so you would assume it's true in the n by n case and prove it's true for n plus 1 by n plus 1. But that's beyond the scope of what we have at our disposal. Yeah, David? Uh-huh. Absolutely, that's exactly what we're going to do. Yeah, that's exactly it. You can do a bunch of them, right? That's exactly what we'll do. You just got to keep track as you go down the line. Did I just change, did I negate my determinant? Did it stay the same? Did a scalar pop up? And you just got to kind of keep track as you go. Yeah, that's exactly where we're headed. Okay, this third one that I want to, because I think one of these you're going to play with in homework. It's third one, the thing to keep in mind with this scalar is that you're thinking about your factoring out that scalar. So property 3, think factor out. So here's what I mean by that. If you have a matrix 3, 6, 1, 4, right? whatever the determinant of this matrix is, we can think about from this first row like factoring out that 3, right? So if we pull it out of 3, we get 3 times the determinant of the matrix 1, 2, 1, 4. So that's the idea with these scalars, and that's where I'm factoring that guy out, right? So the determinant of this guy is 3 times the determinant of that guy. Cool. Okay, so let's look at this in an example, getting exactly to what David said. So we want to find the determinant of A, and because we want to practice these ideas, what we're going to do is we're going to use our row operations to try to turn the matrix A into a triangular matrix. So then the determinant will be really fast, right? We'll just go down the diagonal. Cool. Okay, so we've got to figure out what we're going to do in order to make this guy. Let me use the word consider. All right, so we're starting with the matrix A. 2, -1, -3, 1, 3, 2, 1, 1, 3. There's the original matrix. Okay, now, because it's always really convenient to have that number 1 in that A11 entry, something we might do is we might want to do a row swap to get that 1 there. Now, if I do that, I can row swap those first 2 rows. So 1, 3, 2, 2, -1, -3, 1, 1, 3, right? So what I did was I swapped rows 1 and 2. Our properties in that last slide said that if I do that, what happens to my determinant? I get a negative. All right, so negative goes up. Okay, so now that I've done that, I'm going to clear out the 2 and the 1 down here like I normally did. Notice this negative is just tagging along now, right? It's going to tag along for a while. So I'm going to clear out. So that'll be what? -2 row 1 plus row 2 and minus row 1 plus row 3. And that will give me 0, -7, -7, and 0, -2, +1. Okay. But I've got my negative that's tagging along from the row swap. Adding a multiple of one row to another does not change my determinant. So it doesn't do anything, right? Okay. Now, if I like, I can take these -7s and factor that guy out, right? So I've got my negative from the row swap tagging along, and then I'm going to factor out, I'm going to pull out that -7 from row 2, excuse me, so that I get a +1 in my A22 entry, right? So factor out -7 from row 2. There it is. And then those guys tagging along, I can do 2 times row 2 plus row 3 to clear out that -2 underneath. Right? So 1, 3, 2, 0, 1, 1, and I get a 0, 0, 3. And that adding a multiple of one row to another does not change my determinant, right? So I've got the negative from the row swap. I've got the -7 from where I factored it out. And now because I have a nice little triangular matrix, I can compute that determinant by multiplying the entries on the diagonal. And we see that we end up with a determinant of 21. Now, I wanted you to see what ones where we went all the way to triangular. But if you also did like this, like got to here, and was like, well, look, why even bother, right? Now I've got a super easy determinant to compute. You don't have to go all the way unless the directions specifically tell you to, right? If the goal is just compute the determinant, and you notice there's a little trick that makes your life easier, then you can stop whenever you're like, okay, easy enough, now I can move, right? So there's that. Okay, now, there's nothing special about row operations. That's what we've done in this class up to this point. We almost always just work with row operations, but you can also perform column operations, and the same rules apply. Let me see. So if you swap two columns, your determinant will get a negative. If you add a multiple of one column to another column, nothing changes. Your term doesn't change at all. And you're also allowed to factor out a scalar from a column, okay, just like you can from the rows. So let's do one example where we do some column operations. And we may not take it all the way to triangular. We may just get to a point where we go, oh, that's easy from here. Let's just do it from here. All right, let me make sure this is on. Okay, so consider the determinant of A is the determinant of 3, 4, negative 2, negative 1, negative 6, 3, 2, 9, negative 3. Let me point something out notationally really fast. Notice, right? I said the determinant of A equals, and then I use the absolute value bars, right? Because this is the determinant of this matrix, right? You don't want to say determinant equals that, because this is a matrix, this is a number. Everybody understand? So now you can, if you want to write like this, you can write determinant of A equals the determinant of this. And that's totally appropriate and correct. Does that make sense? A little bit of the notation there. I'm kind of doing it without saying anything about it. Oh no. Okay, I gotta stop. Cliffhanger. Okay, so we'll pick up with this one on Monday with our column operations and good. All right, good. So we'll stop there. And then we'll talk more about properties like what if you multiply two matrices together, what if you take the transpose, what about the term of the inverse, all that kind of cool stuff. That's what we'll do on Monday. So have a fantastic weekend. Just get your work done tonight. Go ahead and get most of your work done for Monday.
Heller,
I'll see you on Monday. Yeah.
we have one more question. So
Sure.
if you swap rows more than once, do you multiply by -1 again?
You sure do. That's exactly right. Yeah, if you did 2 rows, then it would go back to being positive.
Okay.
That's exactly right. And we'll play with that on Monday, but that's exactly right. Hello. Thank you.
What is it mostly? Because I feel like all we've been learning is like no math, all just history, you know? Yeah. Is it just kind of like using the, is it more so just using stuff in the book and not necessarily stuff in our book?
You too.
I think a little bit both, yeah. They kind of overlap.
I had a question about like the cryptography.
Yeah.
So how would you like decipher like a cryptogram if you didn't have the matrix?
You have to try to crack the code to figure out what the matrix is. So that would be the game. Yeah.
Oh, okay. Also, and then I'm confused. Like, how does if you factor out like the scalar from one row, why does that affect the whole determinant?
Well, so if you think about let's think about like so say you do, say you have 3, 6, 9. We'll do one that we can do like easy. Okay? So if you take the determinant, right, of this matrix, you would get 3 times 2 times 5, right? So 30. Right? Okay, if you think about factoring it out, you can pull that 3 out. That would give me what, 1, 2, 3. So now, from my diagonal, I get the 10, but then there would be the 3 to make the whole thing 30 again.
All right. Okay.
Does that make sense?
Yeah, that makes sense. Thank you.
You're welcome. Hello. How are you?
Good, how are you?
I'm good. I am still learning. Remind me of your name.
I am Stephen.
Stephen, fantastic.
This is the first time I've actually been able to.
Yes, I thought that would be the case, but you know, with the math, it's a little hard to learn names than normally. Well, Stephen, it's nice to see you. Hi, how are you?
Good, how are you?
I'm good. How was Real Tuesday?
Good. We saw some craziness with the, oh my gosh, I'm gonna forget the Taylor series, differentiable versus continuous functions, and like the specialty of being differentiable. It was cool. It's fun to like hear about. I already took history of math, but I feel like we didn't really talk about like. I had no idea who Weierstrass, Bolzano, or anybody really was. It's funny to hear Dr. Pons's like interpretation of that, and like Riemann. It's funny.